Visual illustration of the dynamics of pinhole formation in MLCC end terminations is the result of a joint study between Metoramic Sciences and Palomar Systems and Machines, and should be of special interest to anyone associated with the use or manufacture of multilayer ceramic components. MLCC refers to multilayer ceramic components such as actuators, inductors, varistors, chip resistors, and others. We will focus on ceramic capacitors such as the one shown in this cross-section. The cross-section shows the internal electrodes buried in the ceramic device and how these electrodes make ohmic contact with the end termination. We will be most concerned with defects in this end termination. Normally, these end terminations are either soldered or plated and provide electrical contact between the device and the rest of the circuit. Illustrated here is the most common and economical method of applying end termination ink. Although only one component is shown here being dipped into the termination paste, normally thousands of components are held in a carrier plate and mass dipped in one cycle. In step 1, the chip is being lowered into the termination paste held in a reservoir. Step 2 shows the surface of the paste being disturbed by the insertion of the chip. Note in step 2 that the chip normally does not touch the bottom of the termination reservoir. Step 3 shows tailing as the chip is pulled from the paste. Tailing is a result of the viscoelastic nature of the paste. It is very important that after dipping, this string or tail retracts back up to the chip to yield a smooth surface as shown in step 4. Shown here is a capacitor with good cosmetics. The termination forms a relatively thin and smooth coating on the end of the chip. It is critical to not only have very straight edge bands, but the band widths and overall dimensions throughout a part size should be consistent. When the rheology of the termination ink is not optimized, defects such as the peaking shown here can occur. The overall length of the part is therefore not to design dimension. Placement of these parts into tight tolerance tape cavities is difficult. A number of defects are shown here. Both chips show mooning or non-straight edge bands. In addition, the termination band widths appear excessive and in one case unequal. One chip shows a random pinhole on the side of its band. Depressions visible in the crown of a terminated chip are often referred to as furrows. This defect is usually caused by an improperly formulated or processed termination. The defect most commonly referred to as pinhole is the topic of this presentation. We have identified two types of pinholes formed in multilayer ceramic components by two different processes. The top chip shows the most frequently observed classic pinhole, while the bottom chip shows some random pinholes. Classic pinholes differ from random pinholes by their placement. Classic pinholes follow a normal pattern of placement, frequently taking the two bubble pattern shown here. Random pinholes can be in a variety of sizes and random locations. Classic pinholes are not always obvious. From outward appearances, these unfired terminations appear defect-free. However, dissection shows the classic pinholes are buried beneath the surface. The rheology of many termination inks causes the pinholes to stop at various levels inside the termination. Therefore, a component manufacturer may have no idea that they exist in their product. The problems with classic pinholes can range from a surface cosmetic defect to buried or partially buried voids that can cause electrical degradation. One of the worst situations is where the pinhole partially opens to the surface. When the chip is being plated, ionic plating salts can enter the cavity and begin plating the cavity walls. As plating proceeds, the void will be plated off, entrapping plating salts in the void. Similarly, if the component is to be soldered, fluxes can be entrapped in these voids. These entrapped migratable ionic impurities could threaten the life of the circuit using this component. Completely buried voids or pinholes could lead to loss of ohmic contact, weak pull strength, and possible outgassing problems. It is important to know all types of pinholes normally occur together. Only a small area of a carrier plate loaded with terminated chip capacitors is enlarged to show the presence of pinholes. A typical plate holds nearly 5,000 components. Side lighting was used to make the pinholes more visible. All of these chips exhibit classic pinhole defects. In some cases, only one pinhole is visible. The other pinhole is usually buried just beneath the surface. Classic pinholes are not a random occurrence. They are a serious problem that usually affects more than 80% of the lot being terminated. The many types of defects shown earlier put severe restrictions on the rheology of termination paste. For instance, when dipped, a low viscosity is desired for easy wetting and to allow the tail to level without peaks. On the other hand, a high viscosity is required to prevent the termination from sagging down the chips during drying. This sagging results in non-straight or mooned edge bands. Despite these restraints, termination paste can be formulated for excellent cosmetics. However, a great deal of rheological manipulation over a wide range of values was shown to have very little effect on pinholes. A large number of competitive termination pastes as well as MSI paste were tested in the study, and all created pinholes under normal termination procedures. In addition, a variety of commercial chips of various sizes and compositions were trialed with similar results. Pinholing is not an unusual situation associated with a unique type of paste or chip. There have been several references in the literature attempting to explain the causes of pinholes. Probably the most prominent and accepted explanation is the cavitation theory presented by DuPont. This theory suggests as a chip is pulled from a rather viscous paste, a vacuum is created at the chip's crown, much like pulling a boot from mud. It is theorized this vacuum causes solvents, dissolved air, or humidity in the paste to boil. This boiling results in gas-filled bubbles that remain entrapped in the termination through firing. Another theory, in a paper from Heraeus, suggests powder agglomerates in the paste cause pinholes. Some profess air bubbles entrained in the paste are trapped by the dipped chip, thus forming pinholes. Indeed, this last thought will be shown to be the source of random pinholes. MSI has taken paste processing steps to reduce or eliminate the source of random pinholes. Under very special circumstances, any of these theories may explain classic pinhole formation. However, in reality, none of these theories explain normal classic pinholes. Realizing the deficiencies in the presently accepted theories, it was decided to run a series of experiments to possibly learn the true source of classic pinholes. Palomar and MSI built a prototype terminator which utilized production tooling. This unit differed from standard termination units in that the insertion and withdrawal rates of the dip mechanism was microprocessor controlled. Insertion and withdrawal rates could be varied over a wide range by 1 mil per second increments. Similarly, the chip's position could be controlled to within a mil. Dwell times between movement could be controlled to 0.01 seconds. In addition, any number of dipping movements could be programmed and saved for future use. The experiments utilized commercial paste and chips held in regular production tooling to closely match a production termination process. The experiments were later repeated with a mock termination paste, which showed similar experimental results versus a standard paste. This mock paste used no metal fillers, was transparent, and formulated to be rheologically similar to a normal commercial paste. The mock paste allowed us to observe and film the termination process. The first experiment was meant to approximate a normal termination process. The chips were inserted into the paste at the rate of 500 mils per second, or 1/2 inch per second. The chip was stopped at 10 mil from the reservoir bottom and held there for 1 second before being withdrawn at the same rate as insertion. Chip cosmetics duplicated the cosmetics of normal commercial chips. The chips had good cosmetics, with the exception that nearly all chips exhibited classic pinholes. The next experiment was designed to test the validity of the cavitation theory. The cycle was programmed the same as Experiment 1, except the chips were withdrawn from the paste at the extremely low rate of 1 mil per second. This withdrawal rate was so slow it could not be perceived visually. This would yield the minimum cavitational forces and thus pinholes, if the cavitation theory was valid. However, all the chips exhibited classic pinholes. In addition, they had mooned edge bands and a very thin termination coating. It was decided to try to slow down insertion as well as withdrawal in one experiment. The cosmetic defect of mooning persisted. Due to the slow insertion rate, all classic pinholes were eliminated. The previous experiments suggested pinholes were formed in the insertion step. To test this theory and further refute the cavitation theory, the insertion rate was slow and the withdrawal rate was fast. There were no pinholes formed and the termination coating thickness was normal. Clearly, the experiments show pinhole formation is related to chip insertion rate. This last experiment is identical to the pinhole producing first experiment with just a slight modification. When the chip was several mils above the paste, the rate was slowed. This allowed the chips to enter the ink surface slowly. The rate was again accelerated just several mils below the surface. This resulted in a cosmetically superior chip that was pinhole-free. This schematic shown here is slightly exaggerated to help illustrate the pinhole formation process. The chip is purposely shown skewed to illustrate the fact the chip is never perfectly flat. We observed that upon insertion, one point of the chip touches the termination ink first. If the insertion rate is fast, another point in the chip will also touch the ink and form a pocket or pockets of trapped air. Had the insertion rate been lower, capillary action would have had time to form a wetting front across the chip's face, excluding air before other points of the chip touched the surface. The following experiments in theory were very helpful in controlling pinhole formation. However, it was desired to visually illustrate and record the pinhole forming process. Thus, we used a prototype terminator and a high-speed video camera equipped with special optics, along with the mock transparent termination paste in a transparent paste reservoir. For this experiment, a relatively large 2225 commercial chip was used for better visibility. The first video segment puts the experiment in perspective. What you will see is one chip being dipped into standard termination material from a top perspective view. All insertion and withdrawal rates are fast. The termination tailing or stringing is quite typical. This scene is identical with the last, except transparent termination paste will be used instead of standard termination paste. The clear paste shows the wetting front coming up the side of the chip, and the termination tailing is the same as standard paste. The last experiment will be duplicated. However, you will be viewing the end of the chip from below through a transparent reservoir and termination paste. During the dipping process, two classic pinholes are formed and stay at the chip surface even upon withdrawal. The last experiment will be repeated to show consistency of pinhole formation. The last experiment will be reshown in 2 speeds of slow motion to show how and when the bubbles are formed. It is easy to see the cupping or trapping of a thin layer of air which breaks into 2 stable classic pinholes.